Before you watch this video, you need to be able to effectively draw a Lewis structure for any molecular compound. You also need to be able to predict molecular geometries using VSEPR. This video goes forward to address the concept of polarity. Molecular polarity is very important. The polarity of a molecule greatly affects its chemical properties. Before we discuss polarity of a whole molecule, though, we need to first look at the polarity of an individual bond. Bond polarity refers to the equal or unequal sharing of electrons in a covalent bond. A covalent bond is nonpolar if the electrons are shared equally, like in a diatomic molecule, hydrogen or chlorine, for example. In this illustration, the orange area represents the electron density around those nuclei. Notice that it's very uniform because the electrons are shared equally between these two identical atoms. In a polar covalent bond, electrons are not shared equally. Why would two atoms not share their electrons equally? What's the name of the property of an atom that describes its pull on bonding electrons? That would be electronegativity. When two different nonmetals bond, one element is more electronegative than the other. The more electronegative element pulls harder on those bonding electrons. So the electrons are shared, but not equally. Any covalent bond between two different nonmetals is polar. Look how the electron cloud in this illustration is skewed toward the fluorine. Fluorine, being more electronegative, pulls harder on the bonding electrons. That means the electrons reside more on the fluorine side of the bond than on the hydrogen side. There are two methods used for labeling the polarity of a bond. One method uses a lowercase delta to represent a partial charge on each end of the bond. A polar covalent bond isn't fully positive and negative the way ions are fully positive and fully negative, but a polar covalent bond does have a slightly positive and a slightly negative end. Remember that electron cloud illustration? The electrons reside more on the side of the more electronegative element, fluorine here. One way of noting that is with partial charges, a lowercase delta and a plus on the electron deficient end, and a delta minus on the electron heavy end. The bond polarity is also labeled using a charge arrow. The arrow points in the direction that the electrons are pulled. That's toward the more electronegative element. And to be even clearer, chemists add a line across the arrow on the electron deficient end to make it look like a plus sign on that end. That always goes with the less electronegative atom. These two notations do not have to be used together. You can use one or the other. You do sometimes see both. How evenly the bonding electrons are shared will determine the polarity of a bond. This is determined by the electronegativity difference between the bonding atoms. If there is no difference in their electronegativities, like in a diatomic molecule, that is a nonpolar covalent bond. If the electronegativity difference is an intermediate value, this is a polar covalent bond. Eventually, the electronegativity difference between the atoms is so great that one atom is able to pull the electron entirely off the other atom. What kind of bond does that describe? That's now an ionic bond, because the electrons are no longer shared, they've been fully transferred from one atom to the other. This description of bond types is a little bit deceptive. It isn't quite as simple as three completely distinct types of bonding. In truth, bonding style is more of a continuum. The degree of polarity, which is actually more commonly called the degree of ionic character, varies continuously from 0% ionic character up to 100% ionic. A completely nonpolar bond between two atoms of the same element has 0% ionic character. It is entirely covalent and entirely nonpolar. Other covalent bonds can range from barely polar, a very small percent ionic character, to extremely polar, about 50% ionic character. Eventually, you cross over into the area where bonds are no longer considered covalent at all. The electrons are no longer shared, they're transferred, and it's called an ionic bond. You need to be able to look at any covalent bond between two atoms and determine if that bond is polar or nonpolar. You also need to be able to consider the effect of all the bonds in a structure to determine whether an entire molecule is polar or nonpolar. Most molecular compounds contain polar bonds, but not all molecules are polar overall. To describe a molecule as polar means that the entire molecule has a slightly positive and slightly negative end. A molecule with a positive region and a negative region is said to be dipolar, or it is said to have a dipole moment. For a molecule to be polar, two things must be true. The molecule must contain polar bonds, and its molecular geometry does not allow for polar bonds to cancel. Some geometries allow identical polar bonds to cancel. If you have two identical bonds in a linear molecule, for example, the polarities of the two bonds cancel out, and the molecule is nonpolar overall. It's like an equally matched tug of war. There's no net effect because the poles completely cancel one another out. The same is true for a trigonal planar molecule. This one might be harder to visualize unless you've studied vectors. In a trigonal planar molecule drawn in the orientation we have here, two bonds are pulling up and out. One bond is pulling straight down. If you added the top two poles together into their effect going straight up, it would exactly balance the one bond pulling straight down. If that doesn't really make sense, it's okay. The take-home message is a trigonal planar geometry allows for three identical polar bonds to cancel out, resulting in a nonpolar molecule. A tetrahedral geometry is also symmetrical. All four polar bonds will cancel here as well. The wording here is very important. Bond polarities cancel in some geometries so long as the bonds are identical. Non-identical bonds do not cancel in any geometry. A tetrahedral CH4 molecule is nonpolar because it's completely symmetrical. Four identical bonds are uniformly spaced out around the central atom. All the bond polarities completely cancel out. When one hydrogen is replaced with a different element, though, the bonds are no longer identical. In CH3Cl, the chlorine has a greater pull in its bond than the hydrogens have in their bonds. This results in a net pull in this molecule. The whole molecule is polar. Some geometries allow polar bonds to cancel, but only when the bonds are identical. Some geometries do not allow polar bonds to cancel. If the molecule is non-symmetrical, even identical bonds cannot cancel out because of their orientation around the central atom. A bent molecule, for example, will have a net pull in one direction. In a bent molecule drawn in this orientation, both bonds are pulling out and to the left. There's a net pull from these bonds leftward. The bonds do not cancel out because of their orientation around the central atom. Look at the molecular geometry guide you received with the Molecular Models Lab. Go through the list of molecular geometries and make sure you know which geometries are nonpolar, so long as all the bonds are identical, and which geometries are always polar. Most people can easily see that a linear molecule can be nonpolar. I briefly discussed the trigonal planar geometry earlier. Bonds in a tetrahedral molecule can cancel. Most people also have no trouble seeing the polarities cancel in an octahedral molecule. Every bond has one bond opposite it. The geometry that sometimes causes people trouble is the trigonal bipyramidal geometry. It will help to think of it as a combination of a linear and a trigonal planar geometry. The axial bond polarities can cancel, just like in a linear molecule, and the equatorial bond polarities can cancel, like in a trigonal planar molecule. Always keep in mind that this is all dependent on the bonds being identical. As soon as one outer atom is different, you now have different amounts of bond polarities. Even if the overall geometry is still symmetrical, the quantity of pull is no longer equal. So the whole molecule is polar. It's important that you're able to label a molecule as polar or nonpolar based on its molecular structure. The polarity of a molecule greatly affects its chemical properties, which we will see and use in our next unit of study.